In the example of 8-level quantizer design, we design a uniform quantizer where the signal values range from -8 to 8. We divide this signal range into 8 different regions uniformly and assign one region to one level. And we obtain 8 levels for the quantizer. And we use these 8 levels to represent all the possible values from -8 to 8. So this is the input and output relationship of a quantizer. We can see this is a nonlinear relationship, and also it is a many to one because there are many points here. We only have one values here. The same thing here. There are many values here. We only have one value. These values are not digitized yet. We need to assign the digital bits for each level, and this procedure is called encoding of a quantizer. So encoding is a procedure we're going to assign a sequence of binary bits to the quantization levels. Here we introduce two methods to assign the digital bits to the quantization levels. One is natural binary coding, NBC. Let's use the 8-level quantizer as an example. First of all, we need to design number of bits for the quantizer. So 8 levels, so number of bits V equals to logarithm of 2 number of levels. So in this case, V equals to logarithm 2 of 8. That equals to 3. In other words, 2 to the power 3 equals to 8. If I have 16 levels, that will be 4 bits. So that's 4 bits. This is 3 bits. And we have 4 to the power 4 equals to 60. I use this table to illustrate how we encode the quantization levels. Here, that's the quantization levels, x1 hat, x2 hat, until x8 hat. And here I have level order. I call it 0, 1, 2, until 7. As long as the integer, that's fine. We can start with level 1, 2, 3, until 8. So it doesn't matter. So this is just level order. The natural binary code start with 0, 0, 0. Because for 8-level quantizer, we know we need 3 bits. For next level, for level 1, I use 0, 0, 1, level 2, 0, 1, 0, level 3, 0, 1, 1. Level 4, I use 1, 0, 0. Level 5, I use 1, 0, 1. And the last one, I use 1, 1, 1. It's encoded uniquely. Using this procedure, we finished A to D. This is analog to discrete time conversion and quantizer. And here we have bits, digital bits. Next, let's talk about gray coding. Gray coding has unique advantages in digital communications. We want to encode the quantization levels such that adjacent levels differs only 1 bit. For example, I design 2 sets of gray codes here. I start with 0, 0, 0. Adjacent levels, I have 1 digital bit difference. Here I have 1 digital bit difference. That's 1 here. And then from this level to the next level, I have 1 digital bit difference. That's here. That's this digital bits are different. Then from to next level, I have 1 bit difference. That's here. And next level, I have another 1 bit, only 1 bit difference. And from here to here, this bits are different. Next level, this bits are different. And next, this bit's not different. Each level is represented by a unique code. In other words, the code and levels are 1 to 1. If we receive this digital bits, we know this is level 1. This is a quantization level. It has real values. So this is a gray coding. We want to have only one digital bits difference between adjacent codes. The advantage of gray coding is it's easier for the receiver to correct errors at the receiver in the bits received. There are different sets of gray code satisfy the definition of gray coding. Let's look at this set. I start with 0, 0, 0, and there's a 1 bit difference that's here. The next 1 bit difference that's here. The next one is here. The next one is here. The next one is here. This is the next one. And this is another one. Code 1 and code 2, they are all legitimate gray codes, but they are not the same. So therefore, the scheme of gray coding are not unique. But for each set of codes, if one set of gray codes has been designed, they have to make sure that each quantization levels are represented by different codes. In both sets, in code 1 and code 2, all of these codes are different. They represent different levels. So the codes and levels are one-to-one relationship.